In the last part of this lecture, I want to talk about some of the new technologies that are available for creating new switches. In this course, we're going to cover 4 potential technologies, but there's actually a wide variety of ideas on how to reinvent the transistor. In the next lecture, we're going to talk about tunneling field effect transistors. And the way they operate is that they change sort of the switching mechanism from electrons going over a barrier to electrons going through a barrier. And in the third lecture, we're going to talk about mechanical switches. And that's where you actually physically move a cantilever or a beam in order to switch on and off. In the fifth lecture, we're going to talk about spin. And the idea here is that you use the change in giant magnetoresistance to change a switch, as well as several other possibilities involving spin and new types of switches. But these aren't the only possibilities for switches. There's been a lot of work on cryoelectronics as well. The idea here is that perhaps you could use a superconducting switch, or even just cool down conventional electronics. If something's very cold, your electron can't really jump over a barrier. The challenge here, of course, is that you then have to pay for the cooling. And so in principle, you can still come out ahead, but in practice, I don't believe it's been achieved yet. Another possibility is a recent idea from IBM called the piezoelectric transistor. And the idea here is that you apply a voltage to a piezoelectric, it'll expand, squeeze a piezoresistor, and cause its resistance to change. And in that, you can then get a switching action. And so I'll talk a little bit more about this in a moment. Another interesting concept is negative capacitance. And the idea here is that you put in a ferroelectric into your gate stack, and this actually allows you to get some sort of a transformer or voltage amplification, so that the voltage you see in your channel is higher than what you put on the gate. And again, I'll explain this in more detail. Another possibility is to actually do an electrochemical switch, or I guess what's kind of evolved now into resistive RAM. And the idea here is that rather than moving electrons, you actually move atoms around. The challenge, of course, is that then it's going to be slower because you're no longer moving electrons, and then sort of any sort of chemical reaction will have some sort of an activation energy that you need to overcome. And so these are sort of some of the technologies to address switches. But we can also address the communications part. So potentially, you could switch from wires to optical communications, and that's very helpful for longer wires. Another technology that would be great is if we had a nanotransformer. And the idea here is that, let's say our transistor needs the 1 volt, and there's nothing we can do about it. But if we could then put a transformer on the transistor, we could still operate the wires at low voltage and only increase it where we need it, allowing us to save all the power to charge the wires. I'll introduce one concept for that as to using a mechanical piezoelectric transformer. But this is still not even inclusive. There are several other technologies out there as well. For instance, there are Mott insulators like vanadium oxide that undergo either a phase transition or some sort of a structural change where they change from a resistive to a conducting state, either through pressure or temperature or potentially even electric field. In addition, another possible concept that exists is something called the BISFET, or bilayer pseudo-spin FET. And in this device, the goal is to create sort of a correlated electron-hole pair that acts as a boson, and that you can conduct current through very easily. And then when you apply a little bit of bias, you then break this correlated electron-hole pair and cut off your current. And so there's a lot of possible technologies out there. So now in the rest of this part of the lecture, I'm going to just go through a few of these to kind of give you a little bit of a taste of what else is out there. So this device is the IBM's piezoelectric transistor. The way it operates is you apply this voltage on the gate, this piezoelectric will expand and squeeze this piezo resistor. And you can actually get orders of magnitude of change in resistance as you vary the pressure on it. So in principle, this works. You can actually operate at much lower voltage and much lower power. The challenge, of course, is that we have to now have nanoscale piezoelectrics and piezoresistors, and the material properties aren't that well known once you get that small. In addition, we need high strain, and we need to basically use these materials at nanometer dimensions. And now anything that's mechanical could also potentially have a reliability challenge. And so this is definitely a very promising technology, but there's a lot of work that still needs to be done. Another interesting concept that we recently proposed is called the piezoelectric transformer field effect transistor. And the idea here is that between your wire, you put a transformer, so that way you have a low voltage coming in, and you only increase it where you need it to operate the transistor. And the sort of the principle of operation is that we're going to use a piezoelectric transformer. And the idea is that you apply a voltage to these top piezoelectrics, they all expand, they squeeze this bottom piezoelectric, and you get a higher voltage out on the channel. And so in simulation, we've shown that you can get a 4x to 12x voltage enhancement. Of course, this still has some challenges. First of all, the nanoscale piezoelectric material properties aren't very well known, and they may not be as good as sort of the bulk properties. Anything that's mechanical has a lot of reliability issues. And sort of the current device structures have a low efficiency, around 1%. And so what that means is that this will only be useful for the longer wires, where the wire capacitance and wire energy is what dominates, and not the transistor energy. And so here I want to just illustrate the operation principle in a little bit more detail. So first, let's consider what happens when we put a piezoelectric on the gate of a transistor. Initially, not much. It just acts like a high K dielectric, and you get an extra capacitance in series with your gate. And so it's not very interesting. But now let's try squeezing it. So once we apply this compressive force, we induce a polarization charge, and then this polarization charge will induce an electric field. And what's interesting is that this charge is actually greater than the external charge. And because of that electric field, we get a higher voltage in between the piezoelectric and the gate oxide than what we've applied on the gate. And so this is exactly what we want. We squeezed our piezoelectric, induced some charge, which is then creating a higher voltage than what we applied. So the question is, how do we squeeze the piezoelectric? And so to do that, we just put another piezoelectric on top. So then we apply voltage across here. This one expands, squeezes this piezoelectric, and then that gives us a higher voltage here. And if everything were ideal and there were no losses, we would ideally have a 2-to-1 transformer. It's a promising technology, but it's just right now it's just an idea that has a lot of fabrication challenges and a lot of practical challenges. So another very promising concept is the idea of negative capacitance. And the goal here is to use a ferroelectric gate to get a higher voltage in the channel than what we apply on the gate. And to understand this, let's kind of look at how a dielectric operates and how a ferroelectric operates. So let's consider we have here a dielectric capacitor, and we put some charge across it. So now typically in the dielectric, you're going to have some charge that's induced in the dielectric that tries to screen it. But the key is that this charge will be less than this, and so we'll still have some electric field going across, but it'll be screened a little bit. But now what's interesting is that a ferroelectric actually operates the opposite way. So a ferroelectric wants to spontaneously polarize. But if we now put some charge across it, but we restrict the amount of charge out here, we're actually going to have a larger charge inside the ferroelectric than what we have on the outside. And so the polarization charge is greater than the external free charge. And so what this means is that we're going to actually flip the direction of the electric field. What that's going to allow us to do is to have a higher voltage here than what we have on the channel. Alright, so that's been sort of some of the new device technologies that could potentially solve this problem. And now that we're at the end of the lecture, here are a few review questions to help you go over what we've learned so far. Here are some references on everything that we've covered. So here are some good references on deriving shot noise. Here are a couple of good review articles on new types of transistors. And this is a book that sort of covers many of these new technologies. In addition, here are some of the key papers on the new types of transistors that I've discussed in the last part of the lecture.